kids. Today we're going to talk about section 2.2. We're going to start with example 2. So we're given the limit as x approaches 9. And we have x minus 9 over the square root of x minus 3. And we're asked to find this both graphically and numerically. So I'm going to open up my calculator here, and if we're going to do it graphically, we're going to plug it in like this. Actually, I'm going to delete that. It's good to have parentheses around the entire top and the entire bottom, just to make sure your calculator is interpreting it the way that you mean it to. Okay, so we're going to graph this just to see what it looks like. And what we're doing is we're looking at x equals 9. So that's like right here. And it looks like it's a continuous function. What's going to actually happen though is there's probably a hole right here at whatever value this is. And a way we can verify that, we can say calc, we can go to just value, we can say x equals 9, and it returns no y value, so there actually is a hole there. Now let's talk about y. Probably the simplest solution is if we just plug in 9. What happens? We get 9 minus 9 on top. We get the square root of 9 minus 3 on the bottom, so that ends with a 0. And then this is really just 3, so we get 0 over 0. And that division by 0 will create like an asymptote or a hole often. Now, we can't find the limit just by plugging it in this case. You always want to try that first, because that's definitely the easiest thing to do if it works out. But since we get 0 over 0, we can't do it. Now, we'll learn in the future different algebraic ways to manipulate this. Actually, I'm just going to show you, actually. So we can actually think of this as a difference of squares, the top, which it doesn't immediately look like it is. But what if we thought of it as the square root of x squared minus 3 squared? If we think of it that way, then we can say the square root of x minus 3 times the square root of x plus 3, and then we have the square root of x minus 3 on the bottom still from here. These cancel, and then we have the square root of x plus 3. Now we can apply that limit, and this function will have the same behavior as the original one. So we plug that in. We're going to get square root of 9 plus 3. That's like 3 plus 3. And so the limit is 6, which means the limit of this is also 6. Okay. Now what your book wants you to do at this point is not do it algebraically like that. They want you to look at the left limit, left-handed limit, and they want you to look at the right-handed limit. Now what that means, a limit, remember, is like when we get really, really close to the value of 9 in this case. And so if we want to get really, really close, we're going to look at like 8.9, 8.99, 8.999. And if we do that, if we just plug in these values for the x's over here, we're going to get values like 5.98, 5.99, 5.99. And obviously I'm rounding this. In your book, they take it out to further decimal places. Now, if we're coming from the right side, we're going to be plugging in values like 9.1, 9.0, 9.001, getting closer to 9 but coming from above it and going down. If we do this, we get 6.01. I'll take out one more, I guess, and then 6.001, and then 6.0001. We can see that's close to, we can see these are close to 6, these are close to 6. And so since they're both approaching the same number, if the left-handed limit and the right-handed limit are the same, then we say that the limit is that value. And so this is a way to approximate what the limit would be, and we can see that once again we get the same value of 6. Alright, we're going to move on to example 3. This time we're going to look at the limit as x approaches 4 of x squared. Okay. Once again, the first thing you should always do is just plug in the limit. So the limit as x approaches 4 squared. And so it's just going to be 16. I'm not even going to take this one further. We could do the table method where we plug them in. We could do graphing and we test that value just like we did on the previous one. All of them are going to give us 16. Just move on. Okay, now let's look at example 4. The limit as h approaches 0, 2 to the h minus 1 over h. First thing you should always do with the limit, plug in 0, or plug in whatever it's approaching. Now the problem is there's division by 0, so we can't approach it that way. We're going to just do it graphically is the first way we'll look at this. So clear. What we're going to do, let's see, plug it in, so parentheses, 2 to the x minus 1 divided by x. We graph it, just looks like an exponential function, but we're going to test it at that limit. And we see there's no y value, so there must be a hole in that. So we need to test the left and the right limit. So we're going to see h approaches 0 from the negative side and h approaches 0 from the positive side. So numbers that are close to 0 on the negative side would be like negative 0.005, negative 0.001, negative 0.0001, etc. And you can keep going as much as you need to. Now if we plug these, like if we plug this value in for all the h's on a calculator, hit enter, we're going to get this, this. Okay, so what we see, that's a 9, these are all 9s. We feel pretty confident that it's going to about 0.693 or 0.69, just depending on how you want to round that. Now if we come from the positive side, we're going to get similar values, so they'll just all be positive. And for the values we're plugging in. And then if we do that, we get 0.694, 0.693, 0.693. We see that 0.693 showing up quite a bit. So we should feel pretty confident that they're approaching the same thing on both sides. And so the limit is approximately 0.693. Once again, that would be the y value that that hole is at. Okay, example 5. wants us to investigate the limit as x approaches 0 of sine pi over x. Okay, so first thing we want to do, we want to plug in 0. The problem is that will create division by 0, so we have to move on to trying to do some other method. Once again, we will learn some algebraic methods to do this. This really isn't the one to try it on. So we just do sine pi divided by x. Graph that. The graph of this is really strange. So if you want to look in your book, there's a little bit better visualization of what's going on here. We want to look at x equals 0 specifically, so I'm going to change my window to maybe -1 to 1. And yeah, we'll just do that. Okay, so it looks like it just kind of crosses here. Let's do that quick test. We know it's not going to work out though, but if we plug in x equals 0, there is no y value. Okay, so now we need to test it from the left and the right. So x approaches 0 from the negative side, x approaches 0 from the positive side. So we can just do -0.1, -0.3, -0.007. And on this side, we'll do the same thing, but just positive. Okay, now right here, remember we're taking this, we're plugging it in, and we're going to get a y value. Taking this, plugging it in, getting a y value, and that's what these next values are. All right, these don't appear to be converging to anything in particular. Let's see what happens over here. Oh, whoops, I messed up. This goes to here, this goes to here, this goes to here. Then there was one other value that goes to. Okay, so we actually ended up getting the same values, just the signs are flipped on all of them. Now, both these don't seem to converge to anything, and since the left-handed limit and the right-handed limit are not converging to anything, but specifically not converging to the same thing, we can say that the limit does not exist. All right, moving on to example 6. So this time we get f of x equals x over the absolute value of x as x approaches 0. And then it's asking, does the limit as x approaches 0 of f of x exist? So to do that, we should graph it. And this one I think will be pretty obvious what's going on. We'll see how it looks on here. So we just have x divided by, I gotta find absolute value. No, that's not what I wanted. Second. Catalog, absolute value is the first one. So it looks like that. Graph it. So what this function does, it's just at -1, just a horizontal line, and then it switches right at 0 and goes here. Now, we know that we can't plug in 0 for this because we're going to get 0 over 0, so we can't approach it that way. If we look at the graph though, the graph is just like this. Can't exist at 0, can't exist at 0, but it looks like this. Now if we look at our left-handed limit is going to be -1. So as x approaches 0 from the negative side, we're just going to get -1, -1, -1 over and over. Over here, as x approaches 0 from the positive side, we're going to get 1, 1, 1. And since these left-handed and right-handed limit, or one-sided limits, are not the same, then this limit does not exist. Okay. The function f of x in figure 7 is not defined at c equals 0, 2, and 4. Investigate the one- and two-sided limits at these points. Okay, so I'm going to do my best to draw this. So we kind of have a thing that goes like this, sort of like that. And then up here at 2, a thing that goes like this. Down here is at 2, goes like this, and then continues on. Okay. So we're going to test at each place where it's undefined. So c equals 0. So c equals 0, if we look at c equals 0, we're going to do, so 0 from the negative, so as x approaches 0 from the negative side, and as x approaches 0 from the positive side, we can see that this value right here is roughly y equals 0. So we're either going to start approaching that, or it's going to just give us that exactly. If we look at as we approach, so this is going to be like as we're going like this. This one was like as we were going like this. You can see we end up here. That's where these zeros came from. Right here, we're going to end up at 2. Since these are not the same, we're going to say the limit as x approaches 0 of f of x does not exist. Okay. Now, if we look at as x approaches, so this is for c equals 2 now. As x approaches 2 from the negative side, and as x approaches 2 from the positive side, once again, we don't have, I guess we do have a value. So that's 3, and I think this is 1. Yeah. We can see that as we approach it from this side, the left side, we're going right, but we're approaching that value from the left side. It gets kind of confusing like that. But we're going to get 3. As we approach 2 from this direction, we're going to get a y value of 1. Since those are not the same, we can say the limit as x approaches 2 of f of x does not exist. And the last thing, we're going to look at c equals 4. So once again, as x approaches 4 from the negative side, as x approaches 4 from the positive side, this is valued at 2 right here. So as we go this way, or if we go this way, we see that we're approaching the y value right there of 2 and 2. And so since those are the same, even though the function is undefined, the limit does exist. So the limit as x approaches 4 of f of x is equal to that y value of 2. Okay, we have another example. Example 8. Investigate the one-sided limits graphically. So we have the limit as x approaches 2 from the positive side and negative side of 1 over x minus 2. And if we look at this graphically. Say 1 divided by x minus 2. I would definitely put that x minus 2 in parentheses. We're going to graph it. And my window is left over from the previous problem. It's not ideal. So change that window. Okay. So if we look at this, we can see that if we do the limit as x approaches 2 from the negative side of 1 over x minus 2, and then the limit as x approaches 2 from the positive side of that same function, we're going to look at the graph. So as we get closer and closer to 2, on the left side, we go down to negative infinity, but as we approach it from the right side, we go to positive infinity. So, it only wants us to look at the one-sided limits, but if we were to take it further, we would say the limit doesn't exist for just x approaching 2, because the one-sided limits are different. Now we're going to look at, this is just like this was part A, and then part B of the same one. If the limit as x approaches 0 from the positive or the negative side of 1 over x squared. And let's graph that. We're going to do 1 divided by x squared. Okay, kind of goes up like that. And so set up these limits. Limit as x approaches 0 from the negative side. Limit as x approaches 0 from the positive side. 1 over x squared, 1 over x squared. Move that over there. We can see as we approach 0 from the left side, we're going to positive infinity. Also, when we approach it from the right side, we go to positive infinity. And that's it. Let's see if we have any other examples. No, that's it. So if you have, if you need additional help, please come to Math Lab. Until then, calculator.